In this video, I'll be solving another Math 2A Midterm 1. This was given back in winter 2014. And once again, this was given by one of the lecturers at UCI, and I believe this person still teaches there. Okay, so let's get started right away. We're given this graph of the function f, and we are asked to find all these limits on the second page here. Okay, so let's go one by one. Limit as x goes to minus 2 from the left. So here's x is minus 2. If we approach minus 2 from the left, that's this guy here. And we are approaching minus 2. Minus 2 from the right. We approach minus 2 from the right. It goes to this point here, which is 0. And when we take the limit from both sides, well, we see the limit from the left does not equal the limit from the right. This guy does not exist. Okay? Similarly, when we approach from 2 from the left, 2 is here, 2 from the left is going from there to here. That's approaching the value, minus 3. 2 from the right, that's going up here, which is value 3. And again, two-sided limit. Well, the limit from the left does not equal the limit from the right. This guy, again, does not exist. 3 from the left, that's here. 3 from the left, that's minus 2. 3 from the right, that's to here. And again, that's approaching minus 2. This two-sided limit, well, the limit from the left does equal the limit from the right, so it's the same limit. The limit is minus 2. And finally, we're asked limit as x goes to minus 3. Well, it's continuous here, so that's easy. And we can confirm limit from the left equals limit from the right. That value is 0. Simple as that. Okay? So that's how you do this type of problem. Okay? And now we are asked in part 2, or the next question, to use the same graph. And we're asked to find all points of discontinuity. We're asked to say y, and we're asked to say the type of discontinuity. So once again, continuity, let's state the limit definition of continuity. Let's write it over here. Limit as x approaches to some point p, let's say, at f of x. If it's continuous, then the limit is just f of p. It's as simple as that. That's continuity, okay? So let's write that down first, and then let's go back here. We know it's not continuous here because you can think of it as if you draw the graph, you have to lift up your pen or pencil here. Once again, at this point, at x is 2, and once again, at this point, at x is 3. So let's write that down. X is minus 2, x is 2, x is 3. These 3 points are points of discontinuity. Why? Remember, this is our limit definition of continuity. Well, for the first one, this limit does not exist. So that's our answer. Limit as x goes to minus 2 of x does not exist. That's our reason why for there. It's the same reason for here. The limit from the left does not equal the limit from the right. This limit does not exist. 2 f of x does not exist. For x is 3, that's a different reason. Over here, the function is not even defined at x is 3. So f of 3 does not exist. And that would be this side of the equation. This side is undefined or does not exist. Okay? For types of discontinuity, I don't think that's that critical, but this person asks for it. Over here is jump discontinuity. Let's just say jump. Same reason here, it jumps from one point to another. Jump discontinuity. Over here, it's a whole or a removable discontinuity. You should say removable and that should be fine. Let me cover up the problem over there. Removable and that should be fine. Okay? So that's number 1 and 2. Let's move on to the next problem. We're asked, is f continuous at x equals to 4. Why not? Okay, so we remember we just wrote that this is the definition of continuity. Okay. Well, actually, we don't really need that. By the domain of f, we know that x cannot equal to 4. So that can be our reason. F of 4 does not exist. So no. So not continuous at x is equal to 4. That can be our answer. Okay. Next one, we're asked to find horizontal and vertical asymptotes with these functions. Okay. No work needs to be shown really for these, and that's what the problem says. Okay. Horizontal asymptote. Remember polynomial over a polynomial? We do the degree test. Degree of the top is equal to the degree of the bottom. So we take the leading coefficient, the ratio of the leading coefficients. Y is minus 2/3 would be our answer. Okay. Vertical asymptote. Well, we can factor this bottom as 3 times x plus x squared minus 4. Let's do that. And then this can be factored as x plus 2, x minus 2. So we know we have vertical asymptotes at x equals 2 and x is minus 2. Okay, next one. This guy, once again, we do the degree test. Degree at the top is bigger than degree at the bottom. That means there's a slant asymptote, but we're not asked that. But when there's a slant asymptote, I remember as there's no horizontal asymptote, so none. Or if there's no horizontal asymptote, there's a slant asymptote. I remember it like that. But anyway, besides the point. Vertical asymptote, bottom cannot be 0. So x plus 1 cannot be equal to 0. X cannot equal to minus 1. Meaning vertical asymptote at x equals 1. But actually, that's a trick. Almost got me. Okay, I just realized that this top is factorable. We can factor the top as x plus 1, x minus 1. And then we'd have a removable discontinuity there. So it's not asymptote. So this is none. Sorry about that. Almost got tricked. Let me check that. That's correct. That looks right. Okay. Next, 2x plus 1 over x squared minus 9. Horizontal asymptote, again, degree test. We know the degree of the top is less than the degree at the bottom, so there is a horizontal asymptote at y is equal to 0. A vertical asymptote, this bottom can be factored as x plus 3, x minus 3. So vertical asymptote is x equals 3, x equals minus 3. This one, log base 2 of x plus 1. We know the log does not have any horizontal asymptote. We know the log does have a vertical asymptote. The log of x would be at x equals to 0. This guy is shifted to the left by 1, so at x equals to minus 1, there's an asymptote, vertical asymptote. And just to go back to this one, this is still none, just to clarify, because once again, if we cancel the x plus 1s, well, f of x is x minus 1. That guy is just a line. There's no horizontal, straight line, linear line, no horizontal asymptote. So that's still done. So again, once again, this one was the tricky one in that we had a removable discontinuity here. So it's actually no vertical asymptote. Okay, let's move on. Number 5, we are told that this limit as x goes to 4, square root x minus 2, over x minus 4 represents the derivative f prime of a of a function f at x equals to a. Okay, we're asked to find what f is, what is a. We're asked to compute the limit, and we're asked to find the equation of the tangent line at a, f of a. Okay, and I actually use a different color. I'll try to write big so it's clear on the video. I tend to write smaller, especially when there's lines. Okay, anyway. If you remember, one of the definitions of the limit, of the derivative, limit definitions of the derivative was limit as x goes to some value a, f of x minus f of a over x minus a. This is f prime of a. This was one of the definitions that you might have learned. If not, you can do something similar with the one that you're probably used to. Limit as h approaches to 0, f of x plus h minus f of x over h. It's similar. You can rewrite it in terms of this. But let's just go off of this. This is also the limit definition of the derivative f prime of a. Okay? That's key here. So, if it's the same, let's confirm it's in the same form. If f is square root of x and a is 4, that means f of a is square root of 4, which is 2, that's correct. This a and this a over here are aligned, so it looks like we can just directly take things. So f, as I said, was square root x. A is 4. Let me write bigger. Okay, compute the limit. Okay. So we compute this limit. The trick here, there's probably multiple ways to do this. You can maybe even rewrite it as the limit definition you're used to, but let's just directly use this. We like to use the conjugate. Okay, so we multiply the top and the bottom by square root x plus 2 over square root x plus 2. When we do that, we get limit x goes to 4. This would be, if we for that, we get x plus 2 square root x minus 2 square root x, so those would go away, minus 4. The bottom will have with x minus 4 square root x plus 2. These x minus 4s can cancel, and we're left with limit as x goes to minus 4 of 1 over square root x plus 2. Okay, and now we can plug in x as 4. We get 1 over square root 4 plus 2, which is a fourth. Okay, that's the limit. Okay, now we're asked to find the equation of the tangent line at a, f of a. Okay, so what is a, f of a? A we said was 4. F of a we said was 2. The square root of 4 is just 2, or you can take it from right there. Okay. Oh, it got cut off. Take this from there. Okay, same thing. So we have a point. We need a slope. Well, we actually found slope up here, because slope of the tangent line is the derivative, which we set up here. This is f prime of 4. Okay? We have a slope, we have a point, we can write the equation of a line, the tangent line. X minus 2, we use point slope form, would be, y minus 2 is a fourth, x minus 4. That's our answer right there. This problem doesn't say you have to use slope-intercept form, so you can leave it like that. But let's just do it. Y minus 2 is a fourth x minus 1. Okay, so y is equal to a fourth x plus, not plus 3, plus 1. That's our answer. Okay. So that's that. Let's move on. Okay, here we're told that an object travels along a line, so its position s is modeled by this equation. S is equal to t squared plus 1. The units of s are meters, and then after t, the position is this meters after t seconds. Okay? So, it asks us to find the average velocity into interval 2 and 2 plus h. Okay? Average velocity, how do we find that? Remember, velocity is change in position over change in time. So change in position is s in this case, over change in time. That's v average, we can say. Okay? Change in position, so that'll just be s, let's write it down, s of 2 plus h minus s of 2 over 2 plus h minus 2. So that's the change in time. This is the time interval 2 plus h and 2. So we take the difference, that's the change in time. Change in position, we use this guy, we plug in t is equal to 2, t equals to 2 plus h. That's what we did there. Okay, so when we plug in the 2 plus h into here and h into here, what do we get? We get 2 plus h squared plus 1 minus h squared, 2 plus h squared plus 1 minus, if we plug in 2, that would just be minus 2 squared plus 1, which is 5, so minus 5. Sorry, it's a little messy. All over 2 plus h minus 2, so that's just h. Okay. Simplify, we would get 4 plus 4h plus h squared. That's when we FOIL this guy out. Plus 1 minus 5, that's just minus 4 over h. This 4 minus 4 and 4 here would cancel. We can simplify to, if we divide by h, that would be 4 plus h. That would be our average velocity. Don't forget our units though, that would be meters per second. That's our average velocity. Okay. Now the next part, it asks us to use the answer in part A to find the velocity at t equals to 2. Technically, I feel like this question should be more specific to say, explicit to say that you want to find the instantaneous velocity at t equals to 2. So keep that in mind. We're asked to find the instantaneous velocity at t equals to 2. So how do we do that? Well, we know the instantaneous velocity is when delta t goes to 0 in this average velocity thing. Okay? So delta t was h here when we simplified. So that is equivalent to h goes to 0 of the sky. Okay? So limit as h goes to 0 of 4 plus h. That would be the instantaneous velocity at time equals to 2. This is easy. That's just 4. Units are meters per second. Okay, so that's one way to think about it. Another way to think about it is this looks very close to the derivative. 2 plus h. So we start from time equals 2, then 2 plus some offset h. To find the instantaneous velocity at 2, that means, once again, h goes to 0. That's our derivative. Okay? That's another way to think about it. But here's your answers. Next, we're asked to find limits. So let's do it. Limit as x goes to 5 from the left, e to x over x minus 5 cubed. The hint here is the superscript of this negative sign. If it's 5 from the left or 5 from the right, that's a hint that it's an infinite limit, so let's confirm. If we plug in 5, that's e to the 5, that's non-zero. Bottom is 5 minus 5, which is 0. 0 cubed, still 0. So non-zero over 0, infinity. So we confirmed. Now, is it going to positive infinity or negative infinity? That's the question. So, when we take the limits, we said e to x as x goes to 5 from the left would approach e to the 5. The bottom, as we approach 5 from the left, x minus 5 approaches 0. We're approaching from the left-hand side, so it'll be numbers smaller than 5. So, for example, 4.99. That's smaller than 5. So when we plug in 4.99 minus 5, that would be a negative number. And as we get closer to 5, it'll always be a small negative number. Okay? This sign is positive. This sign is negative. Negative cubed. That's still negative. So we know that this is going to minus infinity. Okay, that's how we do that problem. This one, limit as x goes to 3, 1 over 3 minus 1 over x minus 3. If we plug in 3, we get 1/3 minus 1/3, which is 0. Bottom is also 0, undeterminate. The trick here, if you remember from the other midterm that I solved, as you can see, by the way, it's by the same professor, so lots of the problems look very similar. Anyway, the trick here is to make it one fraction instead of this complex fraction. And how we do that, we can multiply the top and the bottom by 3x. That will get rid of the fraction on the top. So we could say limit as x goes to 3. When we distribute the 3x there to the top, it'll be x minus 3. The bottom we're left with x minus 3 and 3x. So we can cancel the x minus 3's. When we take the limit, we get a 9th. Okay, that's how we do that one. Next, we're asked to find the limit as x goes to minus 4 of absolute value x plus 4 over 3x plus 12. Once again, this looks like the other problem from the other midterm. The trick here is the absolute value of x plus 4 looks something like this. This is minus 4 over here. So when x is less than minus 4, we're on this side of the curve. When x is greater than minus 4, we're on this side of the curve. So we had to break this limit up into 2. Limit as x goes to minus 4 from the left. Limit as x goes to minus 4 from the right. Okay, let me write it out once more. 3x plus 12. This minus is with that, so don't get confused with my messy handwriting. Okay. So, as I said, as we approach minus 4 from the left, is this side. So that curve is negative in parentheses x plus 4. So we write this limit as x goes to minus 4 from the left, minus x plus 4. We dropped the absolute value, but we took the negative sign over, let's just factor out the bottom already. So we're left with this. These can cancel, the limit is just minus a third. Okay, similarly, as we approach minus 4 from the right, we're on the positive curve over here. So we can rewrite this as limit as x goes to minus 4 from the right of positive x plus 4. We drop the absolute value sign. Again, we can factor out the bottom. These would cancel. We're left with positive a third. Well, we see that the limit from the left does not equal the limit from the right. Minus 1/3 does not equal to positive 1/3. So this guy does not exist since the two one-sided limits don't match. Okay, next we're asked to find a and b such that f is continuous for all real numbers. This is the f we're given. Okay. Again, the definition of continuity, let's just write it one more time. Limit as x goes to some value p of f of x should equal to f of p. Okay, so the trick here is we have to make the limit from the left equal the limit from the right in order for the limit to even exist, correct? And then the f of p's can match also if we set a and b appropriately. Okay, so limit. So let's take this seemingly discontinuous thing first to make it continuous. Limit as x goes to 1 from the left, because when x is less than or equal to 1, it's this guy, so 1 from the left, of 2x squared plus a. This guy has to equal to the limit as x goes to 1 from the right. So 1 from the right, so as we approach f of x, as x goes to 1 from the right, we're on this curve, ln x. We want these to be equal in order for this to be able to work. Okay? So this guy, if we evaluate this limit, that's just ln of 1, which is 0. We evaluate this limit. A is some constant, so we can leave that alone. We plug in 1, we're left with 2 plus a is equal to 0. So a is equal to minus 2. We found a. We'll do the similar thing for b. Limit from the left. So x approaches to e from the left of ln x has to equal to limit as x approaches e from the right of b minus x. Like that. Okay? So this limit is easy to evaluate. Ln of e is just 1. 1 is equal to, this limit is easy also, it's just b minus e. Okay, so b is equal to 1 plus e. Okay, so we found a and b. Let me double check that's correct. Yep, that's correct. So a is minus 2, b is 1 plus e. Again, the trick here is we know the definition of continuity, limit as x goes to p, of f of x is f of p. And in order for the limit to exist, the limit from the left has to equal to the limit from the right. So that's what we did for both a and b. Okay. Next, here we're just asked to evaluate these expressions. Okay, so it should be quite straightforward. First one, arctan of -1. Okay. This, remember, when we're finding the arctangent or arcsine or arccosine or something, arc whatever, we're finding an angle. So what angle gives us tangent of what angle gives us -1? Okay. Well, if you remember, arctangent of +1 is pi/4. Okay. That's pi/4 is up here. Tangent is +1. Tangent of pi/4 is +1. -1 would be down here because remember tangent's only defined in these two quadrants, quadrant 1 and 4. So this angle is minus pi/4. That's our answer, minus pi/4. Next, sine of arccosine 3/5. Okay, so remember earlier I just said arccosine or arc whatever is an angle that we're finding. So we can draw a triangle, a right triangle. We have some angle theta that we're trying to find, whose cosine is 3/5. We can rewrite it as cosine of some theta is 3/5. So we can set up a triangle as 3 and 5. And if you remember your special triangles, 3, 4, 5 triangles, so this has to be a 4 over there. Because these Pythagorean theorem will easily find that it's 4. Okay? So this is essentially finding sine of that angle that we just set up over here. What's the sine of that angle? It's just 4/5. That's your answer. Okay? Log base 10 of square root 10. This is using properties of logs. We can rewrite this as log base 10, 10 to the half power. Okay, so we can pull the exponent out. Log base 10, 10, this is easy, that's just 1. So half. Okay, this one, log base 300 minus log base 318 minus log base 350. This is using properties of logs. We know when you have a difference in two log terms, it's the same thing as log base 3 of 100 over 18. Let's keep the second one the same first. We can do that. That's property of log. And then we can apply it once more here. Log base 3 of 100 over 18 times 50. Same thing. Okay, we know that this can cancel with this. That would leave us with 2 on top. This can cancel with this. We're left with 9 at the bottom. So we're left with log base 3 of 1/9. This is the same thing as log base 3. We can write this as 3 to the minus 2 power. Correct? So then we're left with minus 2. Okay. This one, e to the minus ln 5. So remember how here we pulled the exponent out from the log. We can put it back in. So this is the same thing as e to the ln of 5 to the minus 2 power. Same thing. We just put the exponent back inside the log. We can do the inverse. Okay? This is easy because e and ln are inverses. So we're left with 5 to the minus 2 power. Or you can rewrite it as 1 over 25. That's fine too. Okay? Not too bad. Just had to remember properties of logs and all that. Now we're asked true false for the final few problems. If f is a function such that f of 2 is less than 0, f of 5 is greater than 0, then there exists a number c such that f of c is 0. Okay. If you remember, this sounds like the intermediate value theorem. I'm going to say IVT for short. Okay? IVT says if f is continuous, that's the key word, it doesn't say continuous, so we already know this is false. F is continuous, and then within an interval, so for example 2 to 5, there's a point at the end of the interval that is less than 0, and the other point at the other end of the interval is greater than 0. Let me write it like that. If it's, or yeah, like this. If one point is less than 0, one point is bigger than 0, because it's continuous, there has to be at least one 0 crossing. That's what it's saying. It could even have multiple 0 crossings like that. That's fine. But there has to be at least one 0 crossing. That's the big condition, is f is continuous. This doesn't say that, so false. Limit as x goes to 5 is 0, if that is true, and limit as x goes to 5 if g of x is 0, then limit as x goes to 5 the quotient f of x over g of x does not exist. This we know is false, because it's 0 over 0. This is indeterminate. We don't know if it doesn't exist or not. And that's most of the problems we did when we calculate limits. It's always 0 over 0, but we ended up finding a limit, right? So this is false. If limit as x goes to a, f of x exists, but limit as x goes to a, g of x does not exist, then limit as x goes to a, f plus g of x does not exist. This is true. Because it'll be, let's say this is some limit c, it'll be c plus does not exist, so for example, infinity, or even minus infinity, that's still infinity, or minus infinity. So, true. If limit as x goes to a, f of x is infinity, limit as x goes to a, g of x is also infinity, then the limit as x goes to a, f of x minus g of x equals 0. This is infinity minus infinity. This is also indeterminate. We don't know if it actually goes to 0. So false. It's indeterminate for. Lastly, limit as x goes to 2, x minus 2 of x minus 2. These will cancel to 1, so the limit of a constant is the constant itself, 1, so true. Okay? And that's this midterm, so it's not too bad. There were some different questions than the fall 2013, I believe, that one that I did a video on also. So hopefully you can kind of see the new types of problems that appear and just the common ones that kept appearing between the two. Yeah, I don't know what I'm trying to say, what else I'm trying to say right now. So hopefully this video helped. If it did, please give this video a like, and please subscribe to my channel to see more of these types of videos. I'll be doing more midterm 1s, and I have some midterm 2s, and I'll do even the sample exams that they put up on the department also. So look out for those.